Now we move on to talk more about the control map in general. So we've talked a little bit about it. We're going to talk about it more specifically now. So again, we have this control map, and this control map, the way it's expressed here in terms of the state transition matrix, is the general form. So this applies both to time varying and time invariant problems. So in the time invariant problem, B would just be a constant matrix, and so in the time varying case, it's a matrix. Notice, even though in the time invariant case it's a constant, we can't actually pull it out of the integral because in general we need it to multiply by u, which in general is a vector. So this matrix in general will not be the same dimension as this vector, and so we need this in the middle there in order to make that work. So again, the initial value, if we evaluate at the two limits, the two values t0, t0, we get 0. So clearly, if you take the integral from t0 to t0, you get 0. Okay, so that's easy to prove. If you differentiate this, so differentiating this now uses the fundamental theorem of calculus, and again, you can see that kind of thing in the proof of the theorems in the proof section. So using the fundamental theorem of calculus, we're basically taking the derivative of an integral with respect to time. So notice that t appears here and here. So that's why you end up. That's part of the reason why you end up with two terms. But basically, so that's what you're doing, and then you have the limits that you're working with. The transition property again says that if I go from t0 to t2, I can stop at t1 and then pick it up again from t1 to t2. So again, this also follows from the fact that I can just break this integral up from the integral from t0 to t2 into integral from t0 to t1 and then t1 to t2. So this is fairly straightforward to prove. Now, a special case of linear time varying systems is when we have a periodic system. So if A is a periodic, so A is equal to T plus capital T, or capital T is the period. So for example, this matrix is periodic, and the period is 2 pi in this case. That is, this matrix comes back to be the same matrix every 2 pi values of T. So we can use something called Floquet theory that says that for a periodic system with a fundamental solution of matrix solution X, there exist constant matrices S and R, and a periodic matrix P, and a periodic matrix Q, where notice that Q has a period that's twice T, where X can be written as P of T times e to the st, and it can be shown to be equal to Q of T times e to the RT. So we actually have these two different ways of representing the fundamental matrix of solutions. So in this case, the matrix S satisfies this relationship. E to the st is equal to x0 inverse x at time t. Now notice that if x of 0 is just the identity, then this is just x at time t. And so the matrix S satisfies that relationship. E to the st is equal to that quantity. If S is real, so this whole thing doesn't necessarily guarantee that S is going to be real. If S is real, then R is equal to S and Q is equal to P. If S is not real, then we can show that R is given by this expression, S plus S conjugate 1/2, and Q can be written by this expression, x0 inverse x of t e to the minus RT. So we have that. So anyway, that's a special case for periodic systems using something called Floquet theory. So just recapping, our control map in discrete time we saw was just this matrix. Okay, and as k increases, this matrix expands. In continuous time, it's not so much that we have, this basically stays the same shape and structure, it's just that the integral expands. In other words, it goes further along in the integral. So the interval of the integral expands. So this is what we have. So it's clearly the map in terms of how it operates. This is just a matrix multiply. I'm going to take this matrix times the input sequence. Here, I actually have this convolution, so it's definitely more complicated in continuous time. Now, how do we compute solutions? Well, again, we have the three methods that we can use to solve this. In terms of Laplace transform, we saw that if we take the Laplace transform of x dot, that's equal to s times x of s minus the initial condition. And that, taking the Laplace transform of the other side of the equation, x dot is equal to ax plus bu. Here we have ax plus bu, but it's in the Laplace domain. I can now set these two equal to each other and solve for x, and this is what I get. So I saw this last time. And anyway, so this is what I have. I have this inverse times the initial condition, this quantity. So this is the natural response in the Laplace domain. This is the forced response in the Laplace domain. So notice that this is a product of functions in the Laplace domain, the S domain. And so anytime you have a function in the frequency, a product in the frequency domain, that corresponds to a convolution in the time domain. And so here you see the convolution coming out. We also see that the Laplace transform of e to the at is si minus a inverse. Okay, so using transforms, we can see how to do, so this is the convolution in the transform domain. So in some ways, it's pretty straightforward to do. The control map in general, we take the Laplace transform of all of this, we just get this quantity. So again, convolution in the time domain is a product in the Laplace domain. So in summary, the solution of the state equation involves the state transition matrix and the input map in the continuous time as well as discrete time, in the time varying case as well as the time invariant case. The input map is a convolution operator for both time varying and time invariant cases. The state transition matrix for LTI systems can be computed by a number of different methods. So here I say Laplace transforms. It could be either Laplace or Z, depending on whether it's continuous time or not. And so we have a number of different methods. So this is the solution of the continuous time matrix differential equation. Stay tuned for example problems and proofs.